Okay, welcome back. We are looking at another problem in Chapter 15, Chemical Equilibria. The following equilibria were obtained at 823 Kelvin. So we're given two reactions. Okay, and we are given their Kc values. Okay. Based on this data, calculate the equilibrium constant at 823 Kelvin for this overall reaction. So for those of you who have watched the 1210 midterm review, this is very similar to Hess's law with a few differences. So whenever you're given two component reactions and you're asked to calculate some quantity for an overall reaction, you know that you need to combine them somehow in order to build the overall reaction. And then each constant that is associated with each reaction will need to be combined in some way as well to calculate. Again, they're asking for the Kc for this overall reaction. Okay, so let's begin. Let's write our first reaction. We need to get H2 gas and CO2 gas both on the reactant side. So looking at our two component reactions, I see one reaction where the H2 is on the reactant side, so let's start with that. So I'll just be using my finger here instead of the pen. It seems to be writing a little bit better. Okay. So there's our first reaction here. Okay? And we have a constant associated with that reaction. So we do have the H2. That is in our overall reaction. And we do have water. So now again, we need to get the two other species, the CO2 and the CO. We do need to get those in our overall reaction. So let's look at our second reaction above. We do see CO and we do see CO2, but we see these other things. So if we look at our species like COO, this cobalt oxide, the cobalt oxide does not show up in the overall reaction, but it does show up in one of the subreactions. As a matter of fact, it shows up in both subreactions. So let's look at the second subreaction and let's flip it. Let's invert the reaction, making the products the reactants and the reactants products. So our second reaction will be CO2 gas plus CO solid will give us cobalt oxide plus CO2 gas. So we just took the second reaction and we inverted it. We changed the direction. So now we have those two reactants in our overall reaction. So let's verify. We're going to add these. Now remember, when you add, we'll go through it here. So we'll rewrite everything. I will skip the species just to make sure, just to fit everything. Okay. 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 So now we can cross out things that appear on either side of the arrow. So we notice that cobalt appears on either side, and also the COO appears on either side. So we're left with CO2 plus H2 gives us CO plus water. And we look up above, and that matches our overall reaction. So now we need to find the Kc for this. So Hess's law, if you remember from chapter 5, was such that when you added the subcomponent reactions, you could just add the delta H values. However, with equilibrium constants, that's not so. We'll just erase this work here, just so we have a little more room. Okay, so when we add equilibriums, when you add the reaction, you actually multiply the K values. So in this first one, we took this top subcomponent reaction and kept Kc the same. But what about the second one? Remember, we inverted it, we flipped it. So we flipped it. Now in Hess's law, you could simply change the sign. Remember, positive to negative, negative to positive. However, with Kc values, you actually need to take 1 over that value. That's our method of inverting here. We call it taking the reciprocal. And you're still going to multiply. So in the second reaction, because we inverted it in order to get those things to cancel, we need to multiply the Kc value. I'm sorry, we take the inverse. So this is number 1, this is number 2. So we get Kc1 times 1 over the Kc2. Plugging that into our calculator, the overall Kc for the reaction will be 0.137. And again, Kc values are unitless. They are unitless. There is no unit on K values. Okay, thanks for watching. See you in the next video.